I thought I'd talk a little bit about the subjects of things I talked about in the movie, the universe, and our changing picture of the universe. And the wonderful thing about science that distinguishes it from myth is that we are happy, as I said last night, not to understand things, not to know, to have a mystery. It's mysteries that drive us in science. It's the puzzles that make us interested, and our willingness to learn from nature. So this is one of my favorite quotes. I used it in one of my books from Louise Bogan. The initial mystery that attends any journey is how did the traveler reach his starting point in the first place. So what I want to do is bring you today to the starting point of what is probably the greatest mystery in science. And in the process demonstrate the difference between science and myth and the nature of critical thinking. And so therefore use this bit of science as an example of the topics that I know the organizers asked me to talk about. So I'm sorry to, we're gonna have a science class here at noon, and you're free to leave if you wish. One of the reasons it's important to talk about this, to give you a sense of what it's like in my own country, I want to show you a science quiz that was given in a public school in one of the states of my country. Okay, this is a 4th grade science quiz. This person got 100%. They got perfect. The question is, the Earth is billions of years old. Of course, the correct answer is false. Dinosaurs lived millions of years ago. False. On what day did God make dinosaurs? That's a hard question, because if you look in the Bible, it doesn't tell you. But apparently, it's the 6th day. I didn't know that until I saw this. Dinosaurs lived with people. True. What did people and animals eat in the beginning? Plants. That's because in the Garden of Eden, everyone was a vegetarian. Which one fits the behemoth described in Job 40? That's this dinosaur. And if an animal has sharp teeth, it must mean it's a meat eater. You don't see that. False. So this person, young person, has been abused, okay? And why are they abused? Why is this nonsense pervade education everywhere in the world, not just in the United States? And the answer is that somehow people are afraid that knowledge will confront their faith. And they should be to some extent. But it's a sad thing. To me, this is no different, and I say this in my own country, and people are shocked and offended. This is just like the Taliban in Afghanistan. If you are so concerned that knowledge will threaten faith that you don't want your children to learn anything for fear that they'll lose their faith. To me, it's like telling them, we don't want you to learn how to read because you might read Shakespeare, and that might somehow awaken your mind. And it's a sad thing. What I want to try and convince people of is that the universe is a remarkable place. And you should open your mind to the universe. And that if it confronts your faith, there's a problem with your faith. It doesn't mean you don't have to have any faith. It just means that you have to force your beliefs to conform to the evidence of reality, rather than the other way around. And the universe has forced us to change our minds. Another thing that I often say is that science, one of the goals of science is to make us uncomfortable. I like to make people uncomfortable. I like to be uncomfortable. Now that sounds like a bad thing, but being uncomfortable means that you're pushing yourself to your limits. You're forcing yourself to move beyond your boundaries, and that's what the universe does for us. It constantly surprises us. Okay, I think enough preaching. Let's talk about science. So the question of my last book, and a question I'll deal with today, is a remarkable question, which in some sense is a basic question which motivates most religions, which is, why is there something rather than nothing? And as I've often pointed out, when we say the word why, we don't mean the word why. Whenever we say why, we really mean how, or at least we should. Because why presumes purpose. It assumes there's a purpose, but what if there isn't a purpose? So we ask why, why does the heart pump blood? But we don't think it's a purpose. What we really mean is how. What's the physiology that tells us how that works. And if you're a parent, as I've been, you know that why questions go on endlessly, especially late at night just before bedtime. And the only ultimate answer to the series of why questions is because go to bed. And so what I want to talk about is how there's something rather than nothing, and there's lots of ways to look at this. One of the ways is to write a book and begin it like this, in the beginning, and then write a whole book that doesn't explain anything about anything. Okay? Or what you can do if you want to understand the beginning is actually look at the universe. This is a Hubble Space Telescope picture, one of my favorites, but then everyone is my favorite. What I like about this particular picture is that the deep field, every dot in this image is a galaxy. There are, as I said, about 100 billion galaxies in the observable universe. 100 billion. And I'll talk about the change in that picture that we've had in a single human lifetime. And some of these galaxies are 10 billion light years away. That means the light takes 10 billion years to get to us. That means that light, of course, originated well before our sun formed, 5 billion years ago. But it also means, if you think about it, that most of the stars in this picture aren't there anymore. Because the average lifetime of a main sequence star is about 10 billion years. So the light emitted from these stars, they were alive then, but now they're dead. They've burnt out. And any civilizations that are around those stars are now long gone. And similarly, if they look at a picture of us, which they'll see 10 billion years from now, we won't even be a memory. The Earth won't be here, the sun won't be here. Well, the sun will be here, but it'll have long burned out. The reason I tell that little story is that I find pictures like this inspiring. It's amazing the thoughts that they provoke. And that's the other thing that I have to remind people of, is that the science, it fills us with awe and wonder. People often say science takes away from spiritual fulfillment. But this is spiritual fulfillment. And it's better than the spiritual fulfillment of religion, because it's true. And that's a huge advantage. Okay. Now, I want to just bring you up to speed on the modern universe. And it began with this man here, who is one of my heroes. His name is Edwin Hubble. And he gives me great faith in humanity, because he began life as a lawyer and then became an astronomer. So there is hope, even for some of you. And he did many things. The first discovery he made, and I want to point it out to give you an example of how things have changed. In 1925, before the Mount Wilson telescope opened, our universe consisted, as far as scientists were concerned, of one galaxy, our Milky Way, surrounded by a vast, empty, eternal space that had been around forever and would be around forever. That was the scientific picture of the universe in 1925, a single human lifetime ago, 89 years ago. So there are people alive who were alive then. And as I say, now we know that that picture has changed completely, and Hubble helped us do that, because with the Mount Wilson telescope, he was able to see something no one had seen before. Up to that point, when you looked through telescopes, there were these little fuzzy images, which were called nebulae, which is Latin for fuzzy thing. And no one knew what they were. There was a big debate. But with the Mount Wilson telescope, he was able to resolve these fuzzy things and see other island universes, other galaxies. So suddenly, we knew that the Milky Way was not alone. And now, there's 100 billion galaxies in the observable universe in a single human lifetime. What a leap. That's why we are like the early map makers on Earth. We're constantly changing our picture of the universe because we're just at the beginning of understanding. So it's not surprising if we're surprised. And we're constantly surprised. And I'll actually talk today, if I ever get to it, to some results that happened a few weeks ago that changed our picture of reality. Okay, but Hubble made another discovery for which we remember his name, which is more important. He discovered the universe is expanding. So this is what he saw. These are not sperm. These are galaxies. Okay. Although you can think whatever you want if it keeps you awake. But, so what Hubble discovered as he looked out is that galaxies on average were moving away from us. And those that were twice as far away from us were moving twice as fast, and those that were 3 times as far away from us were moving 3 times as fast, and so on. We codify that with something called Hubble's law. So velocity increases with distance. Now, this is a remarkable discovery, because what is it, when you look at it, what does it imply? Well, it implies that we are the center of the universe, of course, right? Look at it. Yet that's not true. I am the center of the universe, but it's not true about anyone else. Actually, none of us are. And the question is, how does this tell us that what it really tells us is that the universe is expanding, not that it has a center. And we can't see that because of our myopic view. We are stuck here in our galaxy. We get a myopic picture, a very special picture that convinces us there's something significant about where we are. And as I said last night, for those of you who were here, that's an illusion. That illusion of significance is something we have to overcome. Now, how can we overcome it? We can overcome it by taking ourselves out of our local situation and trying to imagine what it would be like if we could see the universe from outside, which is not so easy. Some of people last night, I think very late at night, were able to do that. But it's much easier actually to create a 2-dimensional universe, which I've done here, which you can see from the outside. And here I've put galaxies down at regular intervals. And you can see the same image later on. The galaxies are a little bit further apart. So if you're standing outside of this 2-dimensional universe, it's obvious that the universe is expanding. But what would you see if you lived in one of these galaxies? Pick a galaxy, anyone, say this one. To see what you'd see, I just superimpose this image on top of this one, placing this galaxy on top of itself. And what you see is exactly what Mr. Hubble saw. Every galaxy is moving away from you, and those that are twice as far away move twice the distance in the same time, and those that are 3 times as far away move 3 times the distance, and so on. And it doesn't matter what galaxy you pick. You see the same thing from every galaxy. So this allows you to choose. Either every place is the center of the universe or no place is. You can choose, but it doesn't really matter. That's semantics. What it really tells us is that the universe is expanding. And that changed everything. Because a universe that's expanding was once smaller. And if you work it backwards, eventually everything we see was located at a single point. That means our universe had a beginning. In 1929, he discovered that. And of course, a universe with a beginning changes everything, because we wonder about how it began. And we also ask the question, if it had a beginning, how will it end? If the galaxies are moving apart, will that expansion stop and recollapse? Or will it go on forever? Will the future end in fire or ice? And that became the business of cosmology for the 20th century. And it motivated many of us to study this. In fact, the reason I got into cosmology as a particle physicist is because I wanted to be the first one to know how the universe would end. It seemed like a good idea at the time. And you'll see that we've changed our picture about how the universe will end a lot since I began. But the key point is that if it had a beginning, we want to understand how it's going to end. And that requires us to do a little bit of general relativity. Because Einstein's greatest result was his development of the theory of general relativity, which gave us for the first time not just a theory of how objects move through space, but how space itself moves. In general relativity, space is a dynamical thing. It changes in the presence of matter. Space can curve, it can expand, it can contract. All of these things, and that means our universe can be different than we imagined before. It can have what we call a non-trivial geometry. Now, the geometry of our universe can be one of 3 different types. Because our universe can be curved, but I can't draw a curved 3-dimensional universe, nor could you appreciate it, because we're all 3-dimensional beings and we can't picture that. So I can draw 2-dimensional universes, but you have to understand this is just an analogy. But the language is exactly the same. Our universe could be so-called open, closed, or flat. A flat two-dimensional universe is like a flat piece of paper that goes on forever. A closed two-dimensional universe is like the surface of a sphere. And an open one is like the surface of an infinite saddle. Our three-dimensional universe is one of these geometries. Now, if I want to make it clear, I can't draw them, but I can tell you about them. A closed three-dimensional universe is one in which if you look far enough in that direction, you'll see the back of your head. Okay? Because light will go around the universe. A flat three-dimensional universe is not flat like a pancake. It's just the universe you always thought you lived in, where the x, y, and z axes point in the same direction everywhere in the universe. Just the one you grew up thinking you lived in. Whereas in a curved universe, they point in different directions in different places. Fine, that all sounds great at parties if you're trying to impress someone. But what really matters is that if you fill up a universe with matter, in a closed universe it will expand, stop, and contract. An open universe will go on expanding forever, and a flat universe will slow down and never quite stop. And so the business of cosmology was to try and determine which universe we live in. Because once we knew how much matter there was, we'd know the geometry and therefore the future, and that's how I thought I'd discover what the future was. So it's very simple. If we just have to determine how much matter there is, all we have to do is weigh the universe. It's a homework assignment. Okay? It turns out it's taken us 80 years to do it, and I've written a whole book about it at one point. But we can now weigh the universe, and I want to show you how. But I want to take you back in history a little bit, because this lecture is supposed to be about how science is done. So I want to show you how science is really done, and I want to help some of the young people here who may be depressed when they become scientists for the following reason. This is a journal that's a very, very famous science journal, and it's called Science. And nowadays, if you're a young person and you do science and you submit an article to this journal, you will be rejected. And that will depress you. It's okay. I want to show you that it was easier back then. There was it was a kinder, gentler time. This is 1936. And here's how an article began in the science journal Science. This is the title. It's a weird title. Lens-like action of a star by the deviation of light in a gravitational field. Sounds scientific. But here's how it began. Some time ago, R.W. Mandel paid me a visit and asked me to publish the results of a little calculation which I had made at his request. This note complies with his wish. Okay. Try that now and see what happens, okay? Well, the author has some credentials, so maybe that helped. His name was Albert Einstein. Maybe that's why they accepted it. But what he presented was a calculation that he thought was entirely unimportant. He wasn't even going to publish it because he thought it was so important. Earlier, he'd become famous, literally in 1919, by having shown that light, if space curves, light will bend in a gravitational field. And remarkably, in 1919, that was measured. That's what made him famous, okay? Because it wasn't E equals mc squared. No one knew who Einstein was except for scientists. But what was remarkable about that prediction was it was a new prediction for gravity, a new law of gravity. But I think equally important from a sociological perspective, he made this prediction. He made the incorrect prediction in 1914. And it was going to be tested, but happily, the First World War happened and interfered with it. It was useful for him because by 1916, he made the correct prediction. And after the war was over, an English expedition, headed by Sir Arthur Stanley Eddington, tested it by looking at a solar eclipse. Because if you look at the sun, you can't see stars around it. It's too bright. But during an eclipse, you can see stars around it. And if light bends, stars that should be behind the sun actually become visible. And so this British expedition tested this idea by a German scientist after the World War I, and I think that sociology, the fact that they demonstrated that he was right, was the reason he suddenly became a super celebrity in 1919. So great. But he realized that if you have enough mass, and this is this paper, then if you have a source of light behind a huge mass, the light can go around it in both directions and come back and converge and be magnified, like my glasses do for nearby objects. Or if you had a cut glass goblet and I looked at this room, I'd see many images of you. And he realized that space can do just that. It can act like a lens, because space can be curved. But he said it would never be visible, and therefore he thought it was irrelevant. And in fact, here is his calculation in 1936. And what's amusing is if you look back at his papers, in 1912 he did exactly the same calculation, but he forgot he'd done it, because he didn't think it was important. And for me, this is the most interesting thing. If you read the correspondence to the editor afterwards, he said, "Let me thank you for your cooperation with the little publication which Mr. Mandel squeezed out of me. It is of little value, but it makes the poor guy happy." That's how science is done. Because science surprises us. He thought it was an unimportant calculation. It would be totally irrelevant. But it's the way we weigh the universe. Because the very phenomena that he described and figured would never be of use is now allows us to weigh the biggest systems in the universe. And here is the phenomenon that he said would never be observed. This is a cluster of galaxies. Clusters of galaxies are the biggest objects in the universe. They span a distance of about 10 million light years across. So it takes light 10 million years to go from one end of this picture to the other. This particular cluster is located 5 billion years away from us. 5 billion light years away from us. So the light takes 5 billion years to get to us. Great. But you don't have to be a rocket scientist to see that there's these weird blue things in this image that look very different. These weird blue things are multiple images of a single galaxy located 5 billion light years behind that cluster, 10 billion light years away from us, so far away from us that we wouldn't be able to see it, except space magnifies it. It acts like a telescope. And it not only does it magnify it, it produces many different images of the same galaxy. Proof that space is curved. A remarkable image. But of course, we now understand general relativity. We didn't need this proof. We knew that it worked because it had been tested many times. So we can work backwards. We can say, given that image, how much mass must there be in this cluster, and where is it distributed in order to produce the image that you see? That's a very complicated thing called a mathematical inversion that you have to do, but it can be done. And my colleagues, Tony Tyson and others in the United States, about now 2 decades ago, were able to do the inversion, and here's the picture of where the mass is in that distribution. The spikes are where the galaxies are. You can see that. But you can see that while the galaxies have some mass, there's a huge mountain of mass where the galaxies aren't, in between the galaxies. In fact, there's 40 times as much matter in that picture as meets the eye. 40 times as much matter. And in fact, around each galaxy, there's 10 times as much stuff as accounted for just by the visible light. Most of the mass in that image is invisible. It doesn't shine. And physicists have such great creative characteristics that we call it dark matter, because it doesn't shine. But what makes that very exciting is there's so much of it. There's too much of it. There's so much of it that we know it can't be made of the same stuff as you and me. So we know how many protons and neutrons, the stuff that make us up, how many of them there are in the universe. There are independent ways of determining that. There's 10 times more stuff here that can be accounted for by protons and neutrons. So dark matter isn't boring stuff. There's lots of ways you can make things dark. If I turned off the lights in this room, most of you wouldn't shine. Some people who were drinking the stuff they gave last night might. So it could be full of audiences from science film festivals or just snowballs or planets, but it's not that. It's some new type of elementary particle, which means it's going through you and me right here. And we don't have to use telescopes to look for it. We could look for it with detectors in this room. And we're building such detectors, and I was going to talk about that, but it's too early in the morning. I'm happy to answer questions about it afterwards. Because discovering that new type of elementary particle would reveal to us something fundamental about nature. A discovery about the universe tells us something fundamental about the interactions that govern us and maybe our origins. And in fact, the kind of particles that we predict might be the dark matter we're looking for at the Large Hadron Collider, connecting particle physics and cosmology. But it doesn't matter what the particle is here. The question is how much of it is. there. Because if we can weigh clusters, since they're the biggest objects in the universe, if we can weigh them, we can weigh the universe. And images like this have allowed us to weigh the universe. And I'm going to give you the result right now. Okay, here it is. A drum roll. Okay. There it is, right there. There are people in the back that are fainting. They're so excited. What does this mean? Well, physicists, when there's an important number, we always give it a Greek letter to make us sound scholarly. And what this number is this is the ratio of the amount of matter in the universe. It doesn't matter if you can really see all of it there. The amount of matter in the universe divided by the amount of matter that you'd need to make an exactly flat universe. So if omega is less than 1, the universe is open. If it's greater than 1, the universe is closed. And if it's equal to 1, the universe is flat. And finally, after 80 years of trying, we seem to have gotten the Holy Grail, and we now seem to have discovered that the universe is a factor of 3 too small, the amount of matter in the universe is a factor of 3 too small to make a flat universe. Meaning we apparently live in an open universe that will go on expanding forever, and therefore we seem to have answered that important question in cosmology, but there's a problem. The problem is we knew the answer was wrong. Well, we theoretical physicists knew the answer was wrong. We knew what the answer was, because we always know what the answer is. We're not often right, but we always know what the answer is. And we knew that the universe couldn't be open because it had to be flat. Why? Because that's the only mathematically beautiful universe. You'll understand why that beauty exists in a moment. It didn't have to be that way, but that was our bias in advance, that a flat universe was the only mathematical beautiful universe. But these darn observers were doing what observers do so well. They got the answer wrong, we thought. But there's a problem with this image, with this result, because when we weigh the total amount of mass in the universe and try and determine the geometry of the universe, first of all, well, it's difficult to measure the total amount of mass, and this is just around clusters, okay? There's other empty space. What if there's other mass distributions? But also, we have to plug it into the equation of general relativity from the total mass to determine the total curvature. It's a very indirect route. Wouldn't it be better to measure the curvature of the universe directly? And the answer is yes. And the amazing thing is, in the last decade or so, we've been able to do that. I want to show you how. How can we measure the geometry of the universe directly? Well, let me ask you a simple question. How could you measure the curvature of the Earth if you couldn't go to outside space and you couldn't go around the Earth? You're sitting here and you saw a flat Earth. How would you know it's curved? Well, simple. We draw a triangle, and then we ask a European high school student, not an American one, what are the sum of the angles in a triangle? And since you're educated, you know the answer. It's 180 degrees. Okay, but that's because you learned your geometry from Euclid. On a flat plane, it's 180 degrees. But on the surface of the Earth, for example, on a curved surface, I can draw a triangle that's different. I can go along the equator and make a 90-degree angle and go to the North Pole, make a 90-degree angle and come back to the equator. And now I have a triangle with 3 90-degree angles, and 3 times 90 is 270. So all I have to do on the surface of the Earth is draw a triangle that's big enough, and if I can measure the angles and it's not 180 degrees, I know the Earth is curved. And the amazing thing is, the same thing is true for 3 dimensions. In a curved 3-dimensional universe, if I found a big enough triangle and measured it, if the angles added up to 180 degrees, I'd know that the universe is curved. And this has been known for several hundred years, in fact. But only in the last decade or so have we been able to find a big enough triangle. And the big enough triangle comes from the most important observation in cosmology: the cosmic microwave background radiation, the afterglow of the Big Bang. It was discovered by accident in New Jersey, of all places, by 2 people who didn't know what the hell they were doing. But they won the Nobel Prize anyway, because you don't have to know what you're doing to win the Nobel Prize. You just have to do it. And they were actually just at a radio telescope, and they were looking upwards, and they saw some noise. Now, what does that mean? Well, when we look out with telescopes, as I told you, when we look out at distant galaxies, we're looking back in time. So when we look out at galaxies that are 1 billion light years away, we're looking back 1 billion light years ago, billion years ago. If we look 2 billion light years away, 2 billion years ago, etc. Now the universe is about 13.8 billion years old in most places, except in my country, in Alabama and Arkansas and Ohio and a few other places. But in the rest of the real world, it's 13.8 billion years old. A fact which somehow threatens people. But it's true. So that means, in principle, you'd think if you looked out 13.8 billion light years, you'd look back and you'd see the Big Bang. In principle, that's true, but in practice, it's not. Because we can't see all the way back to the Big Bang. Because between us and the Big Bang, there's a wall. Right where that photographer is trying to be invisible. Sorry. I can't see past this wall because it's opaque. If I look out in the universe, as I look earlier and earlier in time, the universe was getting hotter and hotter. And eventually, at a time when the universe was 100,000 years old, it was 3,000 degrees. And at that temperature, the universe is so hot and so dense that it's opaque. You can't see through it. It's called a plasma. And so we try and look past that, we can't see through it. But what happens is, as the universe cools down, below 3,000 degrees, matter becomes neutral. Protons capture electrons. The universe becomes transparent. And if I look out, I can see all the way back to that surface. The same way, if I look out in this room, I can see all the way back to this wall. And a prediction of the Big Bang is that there should be radiation coming at me from that surface when the universe suddenly became transparent in all directions. That radiation was once 3,000 degrees. Now it's, because the universe is cooled, it's 3 degrees above absolute zero. And that's what was discovered by accident in New Jersey. The afterglow of the Big Bang. Now what's great about this is if we were to image this surface, take a picture, we get a picture, a baby picture of the universe. The universe as it looked when it was only 300,000 years old. And I'll show you that picture in a moment. It won a Nobel Prize because it's so important. But on that surface, there's one important scale. That's 1 degree. Why 1 degree? Because this represents a distance on that surface of about 100,000 light years. And if the universe is 100,000 years old, then light can only travel 100,000 light years at that time. And Einstein tells us that no information can propagate faster than light. So nothing over here can affect anything over there at that time. Okay? But more importantly, that means if I have a lump of matter that's that big across, well, it knows it's a lump, it starts to collapse because of gravity, and it heats up, and it does all sorts of neat things. That's fine. But if I have a lump of matter that's this big across, it doesn't even know it's a lump. It doesn't know it's supposed to collapse. In my country, there's a cartoon thing called The Road Runner. Does anyone ever, is that here? Okay, well, for those of you who've seen it, there's always a coyote who runs off a cliff. And he hangs around for a while until he knows he's supposed to fall. It's the same thing here. A lump of matter that's this big across doesn't know it's a lump because gravity travels at the speed of light. And it has to wait till the universe is old enough to know that it's supposed to collapse. So the largest lumps that can have collapsed or begun to collapse are this big across. That gives us a ruler. That's 100,000 light years across. And that gives us a triangle. Because if we have a 100,000 light year across ruler, a known distance away from us, then we can calculate that the angle subtended by that ruler will be about 1 degree in a flat universe. But in a closed universe, where light rays converge as you go back in time, the same ruler will look bigger, maybe 2 degrees. And in an open universe, where light rays diverge as you go back in time, the same ruler will look smaller, maybe half a degree. So all we have to do is look at that surface and look at the lumps and ask how big they are. And that's what we've been able to do and measure the geometry of the universe. Now the first experiment that was able to do that is this one here. It's called the boomerang experiment. It was in Antarctica. And this is a balloon that takes a microwave receiver, because this radiation is in the microwave band. And it took it above the Earth and it went around the world. which is easy to do in Antarctica. If you're at the South Pole, you just do this. But here, it was at the edge of Antarctica, and it took 2 weeks to go around, came back to where it began, and it was therefore called the boomerang experiment. And it took an image of a small bit of the sky in the microwave band to look at that surface. And here's the image it took, okay? This is a false color image. I superimposed the image on top of the original experiment. This is that surface, that baby picture of the universe. And this is a remarkable picture because these are hot spots and cold spots in the microwave background corresponding to lumps of matter. And they're lumps that were probably input at the very beginning of time. They're the lumps that would later collapse to form all the galaxies and planets and stars and aliens and everything in the universe today. But this is before any of them existed. And that's why it's such a remarkable image of the universe. It's a shame when we have such images of the baby picture of the universe, which should inspire and excite all of us. Some people refuse to look at it because it may contradict what they know to be true, which of course is always wrong, if you know the answer before you ask the question. But as beautiful as that is, the question here is how big are those lumps? Because that tells us the curvature of the universe. And to see that, we can do something else. Well, here's better pictures, but I think I'll skip that. Here's the boomerang result, different false color image. And we can create universes on a computer. We can create a closed universe, a flat universe, or an open universe, and we can randomly lay down 100,000 light year across lumps. We can ask how big would they look. In a closed universe, the average 100,000 light year across lump would be that big, but that's bigger than these. In an open universe, the average 100,000 light year across lump would be about that big, but that's smaller than these lumps. But just like Goldilocks, in a flat universe, it's just right. And we now know to an accuracy of better than 1% that we live in a flat universe. The universe is indeed flat. So the first thing we do is this. We pat ourselves on the back. But there's a problem, if you've been awake, and some of you have. About 10 minutes ago, I proved to you the universe was open, because there's only 30% of the amount of stuff needed to make a flat universe. But now we know the universe is flat. So where's the other 70%? Well, if it isn't where galaxies are, it has to be where galaxies aren't. And what is where galaxies aren't? Nothing. That's the first clue. Now, nothing has changed a lot. And some people get upset with that when I tell them that science has changed the meaning of nothing, particularly theologians and some philosophers. Sometimes they differ. And they say, well, you're not allowed to change the meaning of things. But actually, we call that learning. And so science has told us that nothing, namely empty space, is not quite what we thought it was. If you take the laws of relativity and quantum mechanics and put them together, it implies that empty space with nothing in it is not so simple. Empty space is actually a boiling, bubbling brew of virtual particles popping in and out of existence in a timescale so short you can't even measure it. Well, that sounds like religion. Like counting angels on the head of a pin. And it would be. But what people don't realize is science doesn't just tell stories. If it did, it wouldn't be any different than religion. It tells stories that make predictions. And so while we can't measure these virtual particles directly, we can measure their effects indirectly. And this image was actually shown at the Nobel Prize ceremonies in 2004 by the people who'd done the calculations that allowed it to be developed, this animation. This animation describes mathematically precisely what the space inside of a proton looks like. Now, if you went to a good high school, you learned that protons are made of 3 quarks. How many people learned that? So, see, look at this, amazing. Well, we lied to you, like we often do in high school. Protons are made of 3 quarks, but they don't account for most of the mass of the proton. Most of the mass of the protons comes from these virtual particles and fields that are popping in and out of existence. And we can calculate the effects of these. And we can calculate the mass of the proton using this theory, and we come up with the answer that tells us that over 90% of the mass of the proton comes from these fluctuations in empty space. Things you can't see. If you looked there, you wouldn't be able to see them. You'd only see the 3 quarks. But they're there. Okay, great. If they contribute to the energy of a proton, maybe we should consider how much energy those virtual particles would give to empty space. And we can do the calculation. And we do it, we come up with the worst prediction in all of physics. We come up that the energy of empty space should be roughly a gazillion times the energy of everything we see, which is impossible. Because if it were, none of us would be here. In fact, we come up with a prediction that it's 120 orders of magnitude larger than the energy of all the galaxies and all the stars. And as I say, that's literally the worst prediction in all of physics. It's been around since I was a student. The prediction is called the cosmological constant problem. But we knew the answer, because we always know the answer. We knew the answer was 0. Because it's the only sensible answer. Because how could you, if it's not 0, you have to cancel this big number to 120 decimal places and leave some non-zero result in the 121st decimal place. But no one knows how to do that in science. That's crazy. But 0 is a beautiful number. 0 we can get by things called mathematical symmetries, where we cancel things exactly. So all of us were able to go to bed at night knowing there was some new symmetry of nature that none of us understood, but we all wanted to discover, that would explain why this number was 0. So it made us happy. But the universe doesn't care whether we're happy or not. That's another thing that we have to come to grips with. It doesn't give a damn about us. And so since this is science, we can't just stop and say, that makes us happy. We got to determine if that's the real case. So we got to actually measure the energy of empty space. How can we do that? Well, it turns out, many of you who took physics in high school know that gravity sucks. It always pulls. Okay? But if you put energy in empty space, gravity blows. Okay? It becomes repulsive. If you put energy in nothing, and by that I mean you take a region of space and you get rid of all the particles and all the radiation. There's nothing there. If it weighs something, then it's gravitationally repulsive. And it will cause the expansion of the universe not to slow down, as any sensible universe should do, but speed up. Okay. So if we can measure that, we can measure the energy of empty space. And in 1998, two groups of astronomers who didn't know what the hell they were doing, well, they did. They were trying to measure the speed at which the universe was decelerating. To do that, of course, they have to measure objects. They have to measure the Hubble expansion, velocity versus distance, but not nearby, very far away, for objects that are across the whole universe. That's hard. Here, for example, is Hubble's data from 1929. This is velocity versus distance. This is how he discovered that wonderful law. It's also why he was such a great scientist. He knew to draw a straight line through that data set, which is not at all obvious. He was lucky. In fact, he got the answer wrong by a factor of 10, which was an embarrassment. Because if the universe is expanding 10 times faster than it really is, you can work backwards and figure out how old it is, and the universe would be 1.5 billion years old. This was in 1929. But in 1929, we already knew the Earth was older than 1.5 billion years old, except in Arkansas and Alabama and Ohio and other places. And it's really embarrassing when the Earth is older than the universe. It makes us uncomfortable. Now, I point this out because it could have been right. If it had been right, there would be something fundamentally wrong with our picture. And that's okay. We just have to find out what the answer is. It doesn't matter if it makes us uncomfortable. As it turned out, he got the answer wrong. The universe is really expanding about 10 times slower, so it's not 1.5 billion years old. It's closer to 14 billion years old. But the reason he got the answer wrong is it's really hard to do this measurement. Distance versus velocity. How do you know the distance to distant objects if you don't have a tape measure to measure that distance? You have to use physics, and you have to find the right object. I could find the distance to the back of the room by looking at one of those light bulbs and having a light meter in an old camera. And if I know it's 100 watts there, and there's 1 watt of light coming into my camera, I can work out, given how light spreads out, I can find out the distance to the back of the room. So if the universe were populated by 100-watt light bulbs, everything would be okay. But it's not. So we have to look for what we call a standard candle, something whose brightness we believe we know, and then we look at it through a telescope, and we see how bright it looks, and that tells us the distance. That's what he tried to do, but he didn't have a good standard candle. But we now have a good standard candle. Here's one. This is another Hubble Space Telescope picture. It's a galaxy far, far away, long, long ago. Not that far away. It's only about 100 million light years away. And what you see is like our Milky Way galaxy. It's a spiral galaxy. And at the center of a spiral galaxy are about 10 billion stars. What is weird about this picture is this is a single star. And it's shining with the brightness of 10 billion stars. How can that be? Well, it could be a star in our galaxy that just got in the way of the image. But that's not the case. It's actually a star at the edge of that galaxy that's shining with the brightness of 10 billion stars. How could that be? Well, it's a star that's just exploded. A supernova. Supernovae are the most brilliant fireworks in the universe. When a star explodes, it shines with the brightness of 10 billion stars. Fortunately for us, stars don't explode too often. We're here because our sun hasn't. But fortunately for us, they explode. Because as some of you know, and I've said often, you wouldn't be here if they didn't. Because the elements that make up your body came from stars that exploded. Because in the Big Bang, the only elements that were created were hydrogen and helium and a little bit of lithium. Okay? And the importance, for some of you, lithium is important. But for the rest of us, it's carbon, nitrogen, oxygen, iron, all that stuff. And that stuff wasn't created in the Big Bang. It was created in the fiery cores of stars. And the only way it could get into your body and mine, and if those stars were kind enough to explode, spewing those elements out into the cosmos. So every atom in your body has been inside a star that exploded. Maybe more than one star. And as I've often said, the atoms in your left hand could come from a different star than your right hand. You would not be here. You are stardust. You are star children. And to me, that's the most poetic thing I know about the cosmos. And when people say this stuff doesn't matter, it intimately matters to you because you wouldn't be here. You are an intimate part of the cosmos because you came from these stars. And we would not be here if stars hadn't exploded. And to me, that realization alone is worth the whole thing. But in any case, these exploding stars, as wonderful as they are now good standard candles. They allow us, we know, for reasons I can't go into, how bright they are. And therefore, since they're so bright, we can see them in galaxies across the other end of the universe. We can, if a star explodes in a distant galaxy, we can look at it and see how bright it looks, and we can measure the distance to a distant galaxy. And now we've been able to measure such stars. Here's an exploding star. We can look at it. It gets bright for about a month. This will replay. And we can also measure its colors to tell us what kind of star is exploding and all the rest. I won't go into that. And now we can measure the Hubble plot much better. Of course, this is after the realization that on a log plot, everything's a straight line. But even aside for that guide to the eye, we now know the expansion rate of the universe not to a factor of 10, but to an accuracy of 5%. These are nearby supernovae, but the question is, what happens for very distant supernovae that allow us to measure distance versus velocity? And that's what those astronomers tried to do in 1998. And here is the plot they presented. Now, let me just make it simpler. So this is the Hubble law, and let me just draw a straight line and bring the whole thing down here. So a straight line is now that line. If the universe were slowing down, as these astronomers thought it should be doing, these distant supernovae would lay along this curve. But they didn't. They lay even above the straight line. Now, how could we understand that? Well, first, the data could be wrong, because it usually is. Or the expansion of the universe is speeding up. And if the expansion of the universe is speeding up, well, how much energy would you have to put in empty space to fit the data? This curve right here. Well, it turns out you'd have to put exactly what we were missing. If you put 70% of the energy of the universe in empty space, everything works out. 70% of the energy of a flat universe in nothing, then everything works out. But that gives us a picture of a universe that is so crazy, it's changed everything. Because it means that nothing is almost everything. Empty space is the dominant stuff in the universe. And, as I talked about in the movie last night, it means one important thing right away. If you take us and get rid of us and every galaxy we can see and all the stars and the beautiful night sky, get rid of it all, the universe is essentially the same. The universe consists of about 30% of dark matter, about 70% dark energy, and we are a little bit of cosmic pollution left over. You get rid of us and everything we can see and the universe is the same. We are completely irrelevant, and that means that you are far more insignificant than you thought even before you came to the lecture. That is really important because it means clearly the universe wasn't created for us. We are just an irrelevant sideshow. Nothing matters. Our existence is completely irrelevant to the expansion and future of the universe. But this is incredibly exciting because it means we don't know anything. And as I say, science we like to be in that case. The dominant energy of the universe resides in empty space, and the most exciting aspect of it is we don't have the slightest idea why it's there. That makes us happy because it means there's something to learn. We think that its existence is probably tied to the very nature of space and time and the creation of our universe itself, and it will determine our future. So I want to spend the last few minutes talking about our future. How will the universe end? Well, I told you that that's why I got into the business, and we can figure out how our universe will end, and you may hope it'll happen before this lecture ends, or maybe. If I took a coin and I throw it up, it comes back down. If I throw it up higher, it comes back down. And if I throw it up really high, it doesn't come down at all if there's no ceiling. I escape from the earth. Now, we force high school students to learn this by telling them if we take a coin and throw it up, that coin has energy. And this will bring back happy moments for most of you. That energy of the coin has two pieces, a so-called kinetic energy, a positive piece, and a potential energy, a negative piece. And we turn it into accounting. If the positive piece is bigger than the negative piece, if we give it enough speed, the coin will escape. If the negative piece is bigger than the positive piece, the coin will come back down. So it's just accounting. We add up the two pieces. And that's how we determine when spacecraft will leave the Earth and the escape velocity from the Earth. It's a simple calculation. But the neat thing is we can do the same thing for the universe. Take Mr. Hubble's picture here. We're at the center of a region of galaxies. And if the universe is the same everywhere, then in order to figure out what's going to happen to the whole universe, we just figure what's going to happen to a single galaxy. Because if a single galaxy continues to expand forever, the rest of the universe will. If it stops and comes back, the rest of the universe will. So we just look at a single galaxy and we try and determine its total energy. The positive piece comes from its speed away from us, but Mr. Hubble told us that. The negative piece comes from the total amount of mass pulling it back in. And if the negative piece beats the positive piece, if B over A is bigger than 1, the universe will collapse if it's full of matter. If B over A is less than 1, so the positive piece beats the negative piece, the universe will expand forever. But what's amazing is this ratio is nothing other than this quantity omega. And we've measured omega now. The universe is flat. That means omega equals 1. But if omega equals 1, then B over A equals 1. If B over A equals 1, then B is precisely equal to A. But if B is precisely equal to A, the negative piece is equal to the positive piece. And if that's the case, the total gravitational energy of every object in the universe is 0. Now, if you were going to create a universe from nothing, what would you make the total energy? This is the first indication that maybe you can create a whole universe from nothing. And this is a remarkable, plausible result that we've been led to. We live in a flat universe, and that means the total gravitational energy of every object is 0. And that means, potentially, our universe could come from nothing without any supernatural shenanigans. And so I want to just briefly describe to you the kinds of nothing it can come from, and then we'll end and I'll take a few questions. First of all, the first kind of nothing is the nothing of the Bible. Empty space, an infinite void. Well, that kind of nothing is unstable. It'll always create something because these virtual particles pop in and out of existence. But it turns out once you add gravity into the mix, which allows negative energy, you can create particles and antiparticles, and their gravitational energy is negative, and their total energy can be 0, and if that's the case, they can survive forever. So if you wait long enough in empty space, it'll start spitting out particles. eventually enough particles to produce over 100 billion galaxies. So, the question is not why is there something rather than nothing. The question would be why is there nothing rather than something. But that kind of question can't be asked, because if there were nothing rather than something, we wouldn't be here. So it's not too surprising in a universe, an empty universe, that it fills up. That happens automatically. Okay, but that's just a simple kind of nothing, because you might say, well, that's empty space, but where did the space come from? Once you assume, if you assume gravity is a quantum theory, then space itself becomes a quantum variable. And universes can suddenly pop into existence. Spaces and time can pop into existence from nothing. And most of them disappear in a time scale so short you can't measure them. The only universe that can persist forever is a universe with zero total energy. Now you might say, well, that's our universe, but it's not quite the case, because it turned out only a closed universe has zero total energy. Because I told you the gravitational energy of every object in our universe is zero, but that's just one part of the total energy. Turns out the only universe that has zero total energy is one that's closed. But we live in a flat universe. What happened? It turns out that most closed universes that pop into existence will disappear. But if, after a closed universe pops into existence, for a little while, empty space gets energy, then it will expand very fast, fast enough to survive at least 14 billion years. And we predicted over 20 years ago that that's exactly what must happen in our universe. In the very earliest moments of time, there must have been a period of rapid expansion we call inflation, due to ideas from particle physics. But just like blowing up a balloon, if you blow up a balloon very fast, it looks flat. And a universe that gets blown up very early on to a very large size will look flat. So the only closed universe that can survive long enough for us to be here is one that looks flat. Now this is a nice story. It sounds like a fairy tale. But it makes a prediction, and the prediction was just validated 3 weeks ago, in principle, if it's right. Because this theory not only predicts that, but it predicts at the very earliest moments of time, this incredible expansion would generate these fluctuations in space called gravitational waves. We predicted that 25 years ago. And amazingly, that's a prediction you can measure. And in fact, this picture that was just presented 3 or 4 weeks ago has revolutionized the world, if it's right. Because when we look at that microwave background, I told you we look at a universe that's looked 100,000 years after the Big Bang, because you can't see past that, in light. But gravitational waves interact so weakly that gravitational waves created at the very beginning of time can propagate through space and produce effects that we can see today in principle. They can produce effects in the microwave background by distorting what's called the polarization. It doesn't matter. This is the prediction. This is the observation. If this observation is really of gravitational waves, we are looking back not to a time when the universe was 100,000 years old, but these waves were generated when the universe was a millionth of a trillionth of a trillionth of a trillionth of a second old. We are looking back at the beginning of time. We are turning metaphysics into physics. And it is a prediction of inflation that precisely this would happen, and apparently it happened. Validating this picture that I gave you earlier, and telling us that inflation almost certainly happened. If it did, it would force the universe to look flat. So the only universe that can have been created from nothing and survive this long is a universe that looks flat. If you ask what would be the characteristics of a universe that was created from nothing without God, it would have precisely the characteristics we see today. Does that prove that God doesn't exist? No, it doesn't. It just makes God unnecessary, which is a good thing. Okay, I want to end with the last kind of nothing, because it's in honor of my late friend Christopher Hitchens. When I told him this story, he said, you know what? Nothing is heading towards us as fast as it can be. Because if the universe is expanding faster and faster, as it appears to be, then every galaxy we now see will disappear. Because eventually those galaxies will be moving away from us faster than light. And that is allowed in general relativity. So if we wait long enough, the rest of the universe will disappear. And in the far future, it's kind of poetic. This is the Andromeda Galaxy, our nearest galaxy. But remember, 189 years ago, we thought there was one galaxy surrounded by a vast, eternal, empty space. In 2 trillion years, astronomers that evolve around stars in our galaxy, and there will be stars, and therefore organic materials and sunlight and water and life could evolve around those stars. And if life evolves, eventually astronomers will evolve. And they'll build telescopes and they'll discover the laws of electromagnetism and quantum mechanics and general relativity. And they'll look out and what will they see? Nothing. They'll think they live in the universe we thought we lived in 100 years ago. A single galaxy surrounded by an eternal empty space. They will do the best science they can do and they'll come up with the wrong answer. And we are fortunate to live at this time. The only time in which we can observationally verify that we live in a very special time. Which of course is not true. Maybe if we'd lived 5 billion years earlier, we could have seen things we can't see now. Maybe 100 billion years from now, something else. But it is remarkable that these astronomers will see nothing. And then the stars in our galaxy will burn out, and the universe will become cold and dark and empty. And that's the future. And as Christopher put it very poetically, the real answer to the question, why is there something rather than nothing, is quite simple. Just wait. There won't be for long. And I find that the best way to end this lecture because it demonstrates our incredible cosmic conceit. We think we're the pinnacle of evolution. As I said last night, we think it was everything led to us, but we're just one step in a long history that will continue in the future, long after we're gone. And similarly, we think the universe we see today is the universe as it will always be, but it won't be. We're here at a cosmic instant. And the future is miserable, because everything will disappear. So, to conclude, as you heard me say in the movie, 2 things. You are insignificant, and the future is miserable. And that should inspire all of you to be incredibly happy. Because it means, well, science has demonstrated something remarkable. We haven't proved that the universe came from nothing, but it's just like Darwin. We've proved it's plausible. Just like Darwin showed it was plausible that life, the diversity of life, evolved by natural selection and mutation. He didn't know about DNA. It was plausible. We're at that stage now in cosmology where it's plausible that the universe came from nothing. What we mean by nothing has changed, and that's great. And really the important question, as I said, is not why is there something rather than nothing, but the important question is how did the universe evolve and how will we find out? And that's where we're at. This remarkable time in the middle of nowhere, a random time 13.8 billion years after the Big Bang, when we are insignificant and the future is miserable. But we should be happy. Because here we are in this beautiful location with brains that have evolved to allow us to understand the earliest moments of the Big Bang and into the far future. So instead of being miserable, we should revel, enjoy our brief moment in the sun, and use our minds as best we can. Thank you very much. I went on about 10 minutes longer than I planned because I tried, although I speak fast, I actually tried to speak a little slower because I know some of you were listening. But we do have time, maybe 5 minutes of questions.
I think we are okay with 15.
Oh, really? Okay, well, we'll take a few. People have to pee, so we won't take that long. But I'll be happy. I'll be here afterwards, and I promise to sign books and answer questions. So if you're too shy, I can see fine. Yeah. So if you have a few questions now, I'll take 2 or 3 questions or 4, and then I'll talk to you out afterwards. And some of you I'll party with later. So any questions? I think that fellow over there is very excited.
Yes, that's right. Thank you very much. Name's Andre.
Hi, Andre.
Yeah, doesn't matter. So why do you think a religion was created, and what do you think is the future of religion, if I may ask? Thank you.
Well, I don't think, okay, again, you asked the question why. I don't think there was any purpose, but of course I'm not an evolutionary psychologist, but there's a lot of arguments, which I gave last night, some of which, that suggest evolution's, at least in early humans, that religion satisfies an evolutionary purpose. First of all, we are hardwired, as I said, to have what philosophers call a teleological explanation. Namely, we look for purpose in everything. And there's a reason for that, because if if leaves rustle in a tree in Africa a few million years ago, we can either ignore that and be eaten by a potential lion, or look for a purpose to that. So we always look for purpose, even though it isn't there, because it keeps us alive. But religion also apparently, it builds community. It allows certain groups to cohere and maybe defeat other groups. So there's a lot of reasons why we may hold on to religion, and people still do today because it gives us solace. Okay. What I tried to argue is that we don't need it. It serves a purpose, just like xenophobia serves a purpose. In-groups and out-groups serve a purpose. They serve a purpose in blood cells, so you can tell when a foreign substance comes in. They serve a purpose in primitive chimpanzee societies. They serve a purpose in our society, but we can outgrow that purpose and not live in a world of in-groups and out-groups, but realize, because we have brains, we can try and overcome that natural tendency. Similarly, we can realize that it seems to me, that we can build the same kind of cohesiveness and sense of community without religion. Instead of having church services every Sunday, we can have rock concerts, which everyone's happy at, and build people together and all of that. So I don't think it's necessary. It has, we can outgrow it. What will the future be? As I've said before, and I'll say it again, I don't predict the future except for 2 trillion years. In between now and then, I don't know what the future will be. It does look, in the first world, as if it's going away. No matter what people say. Here in the Czech Republic, there are hardly a few believers anymore. Even in the United States, the number of believers is going down. And as in the movie last night, Richard and I have talked and asked if his purpose was to destroy religion or teach science. My purpose is to teach science. I don't care about religion. A byproduct of learning about the universe the way it really is, in my opinion, will be that religion will go by the wayside. But that's not important. For me, the importance is for people to be inspired and amazed at the real universe, and eventually realize that the myths are just irrelevant. And I hope that will happen as we continue to educate people. So my interest is in education, and I think if we look around the world, as education increases, religious belief decreases, and that should be telling us something. Next.
Okay, hi. My name is Thomas. I really enjoyed your talk and the yesterday movie.
Oh, thank you.
Just looking toward future, I also read your paper, Life and Death in the Ever-Expanding Universe.
Oh, okay.
So, just if all the stars are out, there are still the black holes. So I think there was some speculation that we could somehow increase the entropy by feeding the black holes.
Yeah.
Could you imagine some mechanism how this
No.
would work?
No, it's a debate I've had with a remarkable physicist. I think I was talking about it last night. Freeman Dyson and I have had this debate about whether life could exist forever in an expanding universe. And he's very inventive. But we both agree that this awful energy of empty space changes everything. Even if you're incredibly inventive, the energy of empty space will kill us. We live in the worst of all possible universes for the future of life. So once again, so much for a universe created for us. If there was no energy of empty space, the universe would be much more hospitable in the far future. And nothing we can do will change that. If the energy of empty space continues, no civilization can survive forever. Even after stars die, and no matter how smart they are, they can't survive forever. So life will end in an eternally expanding universe if there is energy in empty space. And that's why we live, as I say, not the best, but the worst of all possible universes. So enjoy it while you can. I mean, we can party tonight. It won't happen for a little while. 2 trillion years again. 1 or 2 more questions? Oh, there's someone there with a... Maybe I'll take 2 more. 2 more, okay?
Hi, I would like to ask about your opinion. We just saw an hour ago a film which showed theory about multiverse. It was with Brian Greene, and they showed us the universe as small bubbles or something like that.
Yeah.
So it doesn't seem like a flat universe or something. I would like you to ask your opinion about this.
If I'd had time, and Brian and I actually agree about this now because he's agrees with me. He's come around. It's taken a little while. But in fact, remarkably, the prediction of inflation actually tells us that it's quite likely that there are other universes. It tells us, remember, that on the largest scales, the universe isn't flat. it's actually closed. But more importantly, if inflation happened, it's probably eternal. The universe expands faster and faster at very early times, and some small region leaves inflation. Like if you take water and you stir it and you cool it down below 0 degrees Celsius, it stays liquid. When you stop stirring, it suddenly freezes and it'll break the container because energy will be released. What happens during inflation is energy gets stuck in empty space. But eventually, in certain regions, space relaxes and that energy gets released. Huge amount of energy, creating a hot Big Bang in a small region of the universe. But the rest of what we would have called the universe has continued to expand. That region becomes our visible universe. But everywhere else, space is expanding. And then somewhere else, a universe is created. Or it leaves inflation. And it predicts in this picture that there are universes right now where inflation is ending and a hot Big Bang is beginning. And other universes which are maybe ending. It tells us that it's quite likely that there may be an infinite number of universes. And the neat thing is when the universes leave inflation in different ways, the laws of physics can be different in different universes. And that tells us that maybe even the laws of physics are accidental. And they are what they are in our universe so we could be here. That sounds like design, like the universe was created for us. But it's really cosmic natural selection. Because it says, it's not too surprising to find ourselves living in a universe in which we can live. The opposite would be quite surprising. You could write a whole book about it. It's not too surprising to find out that we can survive in this universe because we can. But it's just like why bees can see the colors of flowers. Not because they were designed to do it, but because if they couldn't get the nectar and they couldn't reproduce. And natural selection tells us that that's how it happens. And life forms that can't survive don't. And so if this is true, it says, well, we're just an example, if you wish, of cosmic natural selection. Our universe has the properties it does because we're here to observe it. Physics, God forbid, if you'll excuse the expression, becomes an environmental science. The laws of physics are accidental. Now, that may or may not be true, but it is a fascinating possibility. But we have been driven to this idea of a multiverse, as I said in the movie, not because we like it, but because the laws of physics are telling us it's likely. And for me, as I think I said in that movie, it's interesting that the multiverse in many ways plays the role of God. People invented God because they wanted something outside of time, something that was eternal, something that was beyond the laws of our universe. Well, a multiverse is just that. If the laws of physics are different in every universe and the multiverse is potentially eternal, it satisfies everything that God does. But much more relevant, it's actually well motivated. And so there's no need for God, and it's not as if we should worship a multiverse. If it's true, we have to get used to it. As I said, I don't even like the idea. But we'll find out. Because if we can actually test this idea, measuring these gravitational waves, and test the models of inflation, we can actually test the physics that implies there may be other universes. And while we will never know about them directly, it's like knowing about the existence of atoms. In 1905, we didn't know that we couldn't see atoms, but all the indirect evidence told us was there. And if we have a theory that explains the properties of our universe, 50 different observables, but one of the 51st predictions is that there should be other universes, if it gets all the other 50 right, we're likely to accept it. So it becomes not metaphysics, but physics. And that's fascinating. And we'll wait and see. In your lifetime, we'll potentially know. And that's fascinating. Now that's profound, and I would end it that way, but it looks like you've given... Have someone else got the microphone? Do you have a really good question? Okay, we'll end on your question. It better be really good, because that was really profound.
I'm hoping. Did I get it right that you said that if we by ourselves create some kind of empty space by getting rid of all the particles, etc., if there is a real vacuum there, is it right to say that some kind of matter will arise out of there?
Eventually, if you wait long enough, the laws of quantum mechanics say yes, that would be the case. But, yeah, so yes, you'd see real particles popping spontaneously into existence. Similarly, if you wait long enough, the new universes should be created. Now you might say, well, how come we don't see them? Okay? And the answer is, well, it's kind of interesting. If space suddenly appears, if we create a new space, a closed universe, even if it occurred in our space, it doesn't have to. From the outside, it would look like a black hole that would collapse. From the inside, it would get bigger. It's a wonderful thing about general relativity. From the outside, it looks smaller, and eventually it would decouple from our universe. So a microscopic baby universe that spontaneously creates would in an instant disappear from our universe, so we'd never see it. And so it's quite possible that new universes